Hi everybody, I'm Karl Majorhazi from Stats NZ and I'm here to talk to you about population grids. This is because back in 2015 we asked users of our statistical geographies whether they would use a population grid and got an overwhelmingly positive response. Now we're working towards adding grids to our statistical standard for geographic areas. Here's a list of all the types of organisations that said yes to population grids back in 2015. Gridded data is not new. There's plenty of products around the world. We've even published some gridded data ourselves to help prove the concept. But now we want to make grids an official part of Stats' framework. The European Union, as part of their Geostat project, mandated that all their member countries produce a 1 kilometre population grid, 1 kilometre being the most suitable at the continental level. You might remember the map that Andrew Douglas Clifford put together to show where nobody lives. This got some media attention and ours as well, because it helps highlight a problem that we have visualizing population data by the traditional statistical areas. Compare the gridded map to a statistical area map that shows the same thing and you see the problem. Statistical geographies simply aren't designed to show where people don't live. We're not the only ones to see this issue. Take a look at Australia's comparison of their statistical geographies and the gridded version. Our statistical maps look that way because we use this framework of statistical areas. It was developed back in the 70s and is the backbone of statistical publications. Each area is drawn to encapsulate a target population size, 100 to 200 people in the orange areas, 1,000 to 4,000 people for the blue areas. You can tell urban areas because the shapes are smaller, indicating that population density is higher. In areas where there are low population densities, those statistical areas have to be made bigger, and that's why they incorporate a lot of unpopulated land. So let's compare the two ways of mapping population in the Waikato and Bay of Plenty. This is population data mapped by its statistical area, in this case SA1. Note the narrow colour bands. I've broken the rules as a deliberate attempt to make the map look even more confusing. But if you notice the large dark green area right in the middle of the map, it has a higher population relative to those around it, but that's only because the shape has been drawn bigger to try and meet that target population size. So let's compare the same data converted to grid. This seems to me to be much more representative of where people actually live and where they don't live. And this is something we want our official statistical releases to show. So let's compare the two different resolutions of grid with the SA1s and SA2s. Note that the SA1 and SA2 shouldn't be considered higher or lower resolutions of each other. They are just different ways of slicing up the same underlying data. It's an example of the modifiable area unit problem, where the patterns you see in the data are driven by the geography and not the data itself. If you compare that to the grids down below, the higher and lower resolution ones, they carry the same broad spatial patterns within the same resolutions. Let's take a closer look at the settlement of Ruatahuna. We can see the difference the gridded representation shows you to the statistical one. That thick orange line you see that goes right through the community is the boundary of two SA1s. The yellow dots are address points, or a surrogate for dwelling, and they pretty much are split by the statistical areas. The coloured squares are the 250 metre grid cell populations. So this gives you a really good idea at a detailed level the difference and applicability that gridded data has over statistical areas. So let's just round up the grid format. It's great for spatial analysis and visualization because it's normalized by land area. We're talking things like access to services, emergency management planning, infrastructure planning, public safety. They are a fixed geography, which means that once we've set the specifications, we don't have to modify them at all in the same way we do with statistical areas. We've seen that patterns in the data are visible throughout the different resolutions. Of course, it shows where people aren't, which is important to some applications. It's a good way of linking with other data, particularly in rural areas. And it minimises the modifiable area unit problem. We start by setting up the grid framework. A square grid, which seems to be the most basic type of grid we can produce, at 1 kilometre, 500 metres and 250 metre resolutions to cover a whole multitude of applications. It goes out to the 12-mile limit and includes the Chathams, even though it's an NZTM projection. Once we've set the grid framework, we have to put some data into it. But there's a catch, and this is the bottom line when it comes to confidentiality. Grids have a lot of small areas with low population counts that under the confidentiality rules that we apply to statistical areas, they would be suppressed. This doesn't make for a very useful data set. So we have to find the right methods to put data into the grid. Here are some methods for adding data to a grid. The first one is to aggregate the raw data, that is, the locations and the populations at those locations. The problem with that is that it falls foul of our confidentiality rules. The second one is to disaggregate from already published, aggregated and confidentialized data. This is by far the safest way to work. The third one is to aggregate data from locations and then confidentialize. This is similar to the way we work with our statistical geographies by random rounding or adding some noise. The fourth method is to confidentialize the locations and then aggregate the data. This is quite efficient because we only need to do confidentiality once, and confidentiality can just mean swapping records and or adding some noise to that. The last one is to build a spatial model from the location data. It's something we do in environmental information all the time. You're not getting population counts, you're creating estimates for each grid cell though. We'll be using the disaggregation method to start with because it's safe and doesn't do a bad job. So the first step in that is to work out the number of locations or dwellings that exist in each statistical area. Then you divide the population by the number of locations to get a population per point. Then you assign that population back to the location point data from which you can aggregate those populations to the grid cells. 3 spatial joins and a bit of a calculation and you're done. This is what it looks like in real life. The SA1 data is in the green colours. The black dots are the address points. The grey shapes are the building outlines for a bit of context. So I'll finish with another perspective on the difference between statistical areas and grids. This is what you see if you extrude the SA1 population as height. And this is what you would see if you were using a 1 kilometre grid and its population as height. It's a much more realistic representation of population distribution, and this is what we want you to have at your disposal. So we're keen to hear your ideas, your feedback for this proposal. Thank you for your time.